In this video, we're going to talk about carbohydrates. So what exactly is a carbohydrate? Well, early chemists thought of them as hydrates of carbon. So consider the molecular formula of glucose, C6H12O6. If you divide every subscript by 6, you'll get C1H2O1 or CH2O. And so that looks like carbon plus water. Thus we have the name carbohydrates. And carbohydrates, they're used to store energy. And so it's very useful. It's a very important biomolecule. Now, the first term you need to be familiar with are the monosaccharides. So these are the simple sugars like glucose, fructose, galactose, mannose, ribulose, xylose, and things like that. But the most common monosaccharides that you will encounter are these two, glucose and fructose. Now, the next term you need to be familiar with is a disaccharide. A disaccharide is basically the combination of two simple sugar units. For example, sucrose is a disaccharide. Sucrose is the combination of glucose and fructose. Another disaccharide that you need to know is maltose. Maltose is the combination of two units of glucose. And then we have lactose, which is glucose plus galactose. Now, the next term that we're going to talk about is a polysaccharide. A polysaccharide is basically a polymer, and a polymer is a long molecule with many monomers or units. Two common polysaccharides that you need to be familiar with are starch and cellulose. Starch is found in animals. It's used to store energy, and cellulose is found in plants. It serves a structural purpose. Now, both of these polysaccharides, they contain thousands of glucose monomers. So glucose is the main monosaccharide or the main unit that comprise these two polysaccharides. So since glucose is so important, let's draw the Fisher projection of it. So glucose has an aldehyde functional group. You can see the CHO at the top. And it's basically a polyhydroxyaldehyde. It has many hydroxyl groups, and it also has many chiral centers. So this is called D-glucose. Now, if you see the word D, what it means is that at the chiral carbon at the bottom, that is away from the aldehyde functional group, the OH group is on the right. Now, let's say if we drew the same structure, but if the OH group was on the left, then this would be the less common L-glucose. So if the OH group is on the left, you get the L isomer. But if it's on the right, you get the D isomer. The D isomer is the one that's most commonly found in nature. Now let's draw the structure of fructose. There's going to be some similarities and some differences. The biggest difference is the functional group. Fructose has a ketone functional group, whereas glucose has an aldehyde functional group. And so that's the biggest difference that you want to pay attention to. You don't want to get that wrong on a test. So this is the structure of D-fructose on the right. And you can see why it's D because, once again, we have the OH group on the right side at the bottom chiral carbon. So glucose is an aldose. When you hear the word ose, that means that it's a sugar. Glucose, fructose, ribulose, xylose, they all end in ose. And then the aldehyde or aldehyde part or the ALD I was trying to say, it tells us that we have an aldehyde functional group. So it's an aldose. Can you guess what fructose is? Well, since we have a ketone functional group, fructose is a type of ketose. Now, because we have a total of 6 carbons, think of 6 as hexane, glucose is called an aldohexose. It has an aldehyde functional group, it has 6 carbons, hexane, and then ose is a sugar. So it's a, let's see if I can fit that in, an aldohexose. Fructose is a ketohexose. It has the ketone functional group, it has 6 carbons, and so it's a ketohexose. Now the next thing that we need to talk about is a term called epimers. What do you think epimers are? To illustrate this concept, I'm going to redraw glucose and an isomer of glucose, which is galactose. There's many isomers of glucose, but I'm going to focus on galactose. So on the left, this is, as we said before, D-glucose. Now galactose has a very similar structure to D-glucose. In fact, everything is the same except one part of the molecule. And do you see where it is, where the difference occurs? So this is D-galactose. And both of these are the D isomers because, as you can see, the OH group is on the right. Now, notice that the only difference between glucose and galactose is the configuration at these 2 carbon atoms. Notice that the OH group is on the right, and for galactose is on the left. And so therefore, these 2 molecules are known as epimers. Epimers are diastereomers that differ only at 1 chiral center. Now, in order to have diastereomers, the 2 molecules has to differ at least 1 chiral center or more, but not all of them. But in the case of an epimer, they can only differ exactly at 1 chiral center. Now, this is carbon 1, 2, 3, 4, 5, and 6. And so galactose is known as the C4 epimer of glucose, because at carbon 4, that's where galactose differs from glucose. So make sure you understand the term epimer. Now, it turns out that only a small amount of glucose exists in a straight chain form. The majority of it exists in a cyclic form. And so what we're going to do is we're going to draw the cyclic form of glucose. So the first thing I'm going to do is react it with a mild acid to activate the aldehyde. And so we're going to get a structure that looks like this. So here's the carbon with the aldehyde functional group. Let me draw it this way. And right now it has a hydrogen on it, a positive charge, and a lone pair. And let's draw everything else. So the OH group on carbon 5, so that is this carbon here, is going to attack the aldehyde carbon, or the carbonyl group, breaking this pi bond, turning it into an OH group. And so whenever a molecule reacts with itself, it forms a ring. But before we form the ring, let's do this one step at a time. In order for the OH group to attack the carbonyl carbon, the molecule has to bend into the right form. And so let's draw it this way first. So this oxygen still has a positive charge at this moment. Now, this is going to be carbon 1, and here we have carbon 2, 3, 4, 5, and 6. Now, carbon 2 has the OH group on the right side. So when converting that into its cyclic form, you need to put the OH group in the downward direction, which means H is going up. Now, for carbon 3, the OH group is on the left side. So in this case, it needs to be facing upward in the cyclic structure. Now, for carbon 4, it's on the right side. So therefore, it has to be going in the downward direction. And at carbon 5, the OH is on the right side, so it's also in the downward direction. So this is what we initially have. Now, in order for the OH group to basically attack the carbonyl carbon, it has to be in the right position. It has to be in this position. So we need to replace these two groups. So what we're going to do is we're going to rotate this portion of the molecule in a counterclockwise direction. So the OH group is going to be here, and then the CH2OH group will be here, and the hydrogen will be there. So let's get rid of a few things. So now the hydrogen is going to be in this position. The CH2OH group is facing the top now. And now here's the OH group. This explains why the hydrogen is in a downward direction, because typically, if we look at this, here the OH is on the right, and so that should be on a downward direction, but here the H is on the left, and so that should be up instead of down. However, when you rotate it in order to put the OH in the right position, this H is now in the downward position. Because if you look at this structure, you would think that it should be in the upper position, because everything on the left side tends to face up, like the OH group on carbon 3. So that's why the hydrogen on carbon 5 is in a downward direction. So now that the OH group is in the right position, it's going to attack the carbonyl carbon, thus closing the ring. And then the solution will take away this hydrogen. So now we're going to get this structure. Initially, we're going to have a hydrogen here, but we can use water in a solution to take away this hydrogen. So I'm not going to show that hydrogen in the final structure, but just keep that in mind. Now, on carbon 2, we had the OH group facing the downward direction, and on carbon 3, the OH group was facing upward, and on carbon 4, it was facing downward. And then on carbon 5, we have the CH2OH group facing upward and H facing downward. Now on carbon 1, we can get two different forms. The OH group can be in the upward direction, like this, or it can be in the downward direction. And so because we can get both forms, this carbon is known as the anomeric carbon. And these two forms are interconvertible. The OH group, when it attacks the carbonyl carbon, depending on how it attacks it, either from the top or from the bottom, you can get these two different products. But because they're interconvertible, they're still considered glucose. So whenever you have the OH group facing the upward direction, this is the beta anomer. And whenever you have the OH group facing the downward direction, this is the alpha anomer. The beta anomer is more predominant than the alpha anomer. About 64% of glucose in a solution is going to be in the beta form, and the other 36% is going to be in the alpha form, and a very small amount is in the straight chain form, less than 1%, like zero point 0 something. But the majority of it will be in the beta form. Now, there are some other things that you need to know. The specific rotation of beta D-glucose is 18.7 degrees, and that's how much it rotates plane polarized light. And for alpha D-glucose, the specific rotation is 112.2. And let's say if you take pure beta D-glucose and you dissolve it in water, the specific rotation will change from 18.7 and it's going to go up to 52.7. Likewise, if you dissolve alpha D-glucose, it's going to decrease from 112.2 and it's going to stop at 52.7. And that tells us that in water, both of these two forms exist because the specific rotation of the mixture is between these two numbers, but it's closer to 18.7, and so we're going to have more of the beta anomer and less of the alpha anomer. Now let's talk about the chair conformation of beta D-glucose. Let's see if we can draw it. So let me get rid of a few things here. So how can we convert this into the chair conformation? So let's start by drawing a chair with an oxygen on the inside. It helps if you label the carbon atoms. So this is going to be carbon 5, 4, 3, 2, and 1. So at carbon 2, we have an H in the upward direction, so it's going to be in the axial position, and the OH in the downward direction, so it's in the equatorial position, which is slightly down. And on carbon 3, the H is going to be in the downward axial position, and the OH will be slightly up in the equatorial position. For carbon 4, H is in the axial position, the OH is in the downward equatorial position. And for carbon 5, we have H in the downward axial position, and we have the CH2OH group in the slightly up equatorial position. Now, in order to draw the beta isomer, we need to put the OH group in the upward position, which will be in the equatorial position. So this is the beta anomer of glucose in its chair conformation. If you want to draw the alpha anomer, all you need to do is put the OH group in the axial position and the H in the equatorial position. So this would be the alpha anomer. But let's keep the beta anomer. So why is the beta anomer more prevalent than the alpha anomer? Is it better to put the OH group in the equatorial position or in the axial position? We know that the equatorial position of the chair conformation is always more stable because you minimize 1,3-diaxial strain. And this is why beta D-glucose is more favored at equilibrium than alpha D-glucose. It's because putting the OH group on the equatorial position, it makes the whole molecule more stable. And not only that, but notice that the CH2OH group and all of the other hydroxyl groups, they are all on the equatorial position. Thus, glucose is the most stable aldohexose. And that's why beta D-glucose is so common. It's because of the stability of the chair conformation that it forms. And so glucose is the most common aldohexose. Now, given beta D-glucose, how would you draw the chair conformation of beta D-galactose? Because let's say if you're given a question and you need to draw the chair conformation of another type of sugar. How can you do it? Now remember, galactose is the C4 epimer of glucose. So all we need to do is simply change the chiral center at carbon 4. Everything else, we need to keep it the same. Now we also need to take into account what type of anomer we're dealing with. Since we're dealing with the beta anomer, this is going to stay the same. But if we wanted to draw the alpha anomer, we also have to change that section as well. But let's draw the beta anomer. This might take a while, but I'll get it done soon. So now the OH group has to be facing in the upward direction, and the hydrogen has to face in the downward direction. So this is the only part that we really need to change. And so that's how you can quickly draw beta D galactose. So if you know what type of epimer you're dealing with, then starting from glucose, you can draw beta D galactose. So make sure you really know the structure of glucose and fructose. And from those two structures, you can draw other isomers of those two molecules. Thanks for watching.